Okay, so in this problem, we're told that a 75-kilogram snowboarder has an initial velocity of 5 meters per second at the top of a 28-degree incline. After sliding down the 110-meter long incline, on which the coefficient of kinetic friction is 0.18, the snowboarder has obtained a velocity v. The snowboarder then slides along the flat surface on which mu sub k equals 0.15 and comes to rest after a distance x. Use Newton's second law to find the snowboarder's acceleration while on the incline and while on the flat surface, then use these accelerations to determine x. So we've got a multi-part problem here, and so let's kind of understand what's going on here. So we have this guy, he's going to be traveling 5 meters per second, and he's going to go down this incline, 110 meters, and then once he reaches this incline, he's going to go down this flat part, and he's eventually going to stop, and we're going to try to find that distance x that he stops. So now let's go ahead and start. So the first thing I think we should do is draw a free body diagram. So we're going to label the forces acting on this in order to solve for the different things. So notice what we're solving for. We need to find the acceleration here. We need to find the acceleration here, and we need to find x. So those are the three things that we're solving for. But the first thing we got to do is start at the beginning and draw the free body diagram. So what are the different forces acting on our snowboarder? So we know there's going to be a normal force acting straight up, F sub n, which acts perpendicular to the incline. And so another thing to keep in mind I didn't mention, when we do this problem, it's always good to label your axis. So this right here along this incline, I'm going to designate as the x-axis. Perpendicular to that, I'm going to call the y-axis. So if you look at it like this, imagine this line right here is perpendicular, but this is what we're going to call the x-axis, everything along here. The y-axis is going to be everything along here, so perpendicular to that line. So notice the normal force is going to be along the y-axis. Okay, cool. So that's one of the forces. Another force we're going to have is the force of friction, which acts opposite to the way the snowboarder travels. So we know they're going to go down like this. So the force of friction is going to act along the x-axis here. So we'll just call that F sub F, force of friction. And then the final force we have is the force due to gravity. So the thing about gravity is it acts straight down. So if we imagine this is our person, it's going to act straight down. So we could call this F sub g, or the force due to gravity. But when you do a free body diagram like this, I think it's always important to label the forces in each axis. So we're going to split this problem up into x and y. So we want to have all of our forces labeled in the x and y. So we want to have F sub x. So this is along the x-axis. Right, so this force would be pointing along the x, and then also downwards in the y, we have F sub y. So all we're doing is splitting F sub g into F of x and F of y. So you can call it Fg of x or Fg of y. Just know that these are the x and y component of the force due to gravity. And the reason we do that is we want to have all of our forces labeled in each axis, because that's how we split it up. Okay, cool. So now what we're going to want to do is sum the forces in the x direction. And you'll see why we do this in a second. But essentially, in order to solve for the acceleration, we sum the forces, because we know the sum of the forces in the x direction is going to be equal to mass times acceleration in the x direction, right? So F sub x equals max. We know by Newton's second law, F equals ma. Therefore, all we have to do is just solve for a of x, and then that's going to give us the acceleration on the plane, which is what we were trying to find. So that's why we're summing the forces. Okay, cool. So ma of x is equal to, and now what we do is we look at the forces on the x and add them up. So if you look here, what forces do we have acting in the x-axis? So there's going to be two forces. The force of friction we can see is along it, and I'm going to denote the left is negative and the right is positive. Down is also going to be negative, up is going to be positive. So the force of friction is negative, so I write it there, minus F sub F. And then the other force in the x is our x component of gravity. So we could write plus Fg of x, plus because we know the force is going to the right. And those are the only two forces in the x. The Fg of y is in the y, and F sub n is also in the y. Okay, so now that we've got it like this, we want to solve for max. We have to find the force of friction, and we have to find the x component of gravity. So the force of friction, the formula for it, is something you should have memorized now, is mu sub k times F sub n. So our coefficient of kinetic friction multiplied by the normal force. So writing this out is equal to minus mu sub k times F sub n. So we already know mu sub k. They tell us on the plane that it's 0.18. So we need to find the normal force. We're going to do that in a second. But first, what we're going to find is Fg of x. So how do we find the x component of gravity? So the way we do that is by drawing a little triangle. So let me go ahead and do that right here. So imagine this triangle right here. Let me draw it like this. So this is our triangle. Let me get that line there. Okay, good. So this is our triangle. And what this triangle is, it's essentially this triangle right here. So you can see this triangle, we're just redrawing it. So what you need to know is this angle right here, which corresponds to this angle right here. Let me zoom in a bit so you can see that. This angle right here corresponds to. And you need to know that for an incline, this angle right here is equal to the angle of incline. Therefore, it's 28 degrees. Okay, cool. So we know that's 28 degrees. If you look here and then draw what's on the triangle, this hypotenuse here is this line, which is f sub g. And then fg of y is right here, and fg of x is right there. So we just basically took this and labeled it. And what we're trying to find is fg of x. So in order to find fg of x, we're going to use trig. So the trig function we use for the x is sine. So you should know that the sine of an angle from a geometry is opposite over hypotenuse. So the opposite side to our angle is fg of x. So let's write that here. So sine of an angle equals opposite over the hypotenuse, which is f of g. So multiplying both sides by f of g, you get your fg of x, which is what we want. And so f of g, you should know, is just the force due to gravity, which is just equal to mg. So this really is equal to mg sine of 28. And so we just found fg of x, mg sine of 28. So writing that in here, mg sine of 28. So now we have the x component, and the only thing we're missing here is f sub n. Now how do we find f sub n? So to find f sub n, notice it's in the y direction. So in order to solve for it, I have to sum the forces in the y. So summing the forces in the y, and so it's going to equal to ma of y. But notice that we're only traveling along the x direction. Since this is the x, we only go along this line. Therefore, we don't travel in the y direction. And if we're not traveling in a direction, the acceleration in that direction is 0 because the velocity is 0. So a of y is really 0. And so this whole thing, the sum of the forces just become equal to 0. So then, now that we know that, we just say 0 equals, and once again, like in the x, we're just going to sum the forces in the y. So the two forces we have in the y are f sub n here and fg of y. As I said before, if it's upwards, we call it positive. So f sub n, and then we minus minus fg of y. So what this tells us, moving this to the other side, we'll find that f of n is equal to fg of y. And so if these are equal, we just need to go ahead and solve for fg of y, and that'll give us our normal force. So to find the fg of y, what we want to do is go back to our triangle, and instead of using sine like we did before, we're just going to use cosine. So the cosine of an angle is adjacent over hypotenuse. So the adjacent side is fg of y, and the hypotenuse is f of g. So multiplying both sides by f of g again, you'll get that it equals to mg cos of 28. So the only thing that changed is the function we used. So use cosine for the y and sine for the x. So this tells us f sub n is equal to mg cos of 28. Okay, great. So now we have the normal force going here now. max equals minus mu sub k times mg cos of 28. Right, so this mu sub k times the normal force plus mg sine of 28. And so what you should notice is we have every term here. So we know mu sub k, we know the mass, we know gravity, and all we have to do is really solve for it. And that'll give us our acceleration, which is one of the things they're looking for. So dividing both sides by m, minus mu sub k, so minus 0.18 times the mass, which is 75 kgs. I didn't write that down. I probably should have. So the mass is 75 kg. So 75 kg times g, so g is just the acceleration due to gravity, which is 9.8, times the cos of 28. Let me zoom out a bit. Plus the mass, which is 75, times 9.8, and then multiplied by the sine of 28. And you would go ahead and divide by the mass. So dividing by 75. Okay, great. So now we just got to plug this in. So minus 0.18 times 75 times 9.8 times the cos of 28 plus 75 times 9.8 times the sine of 28 divided by 75. And then, yeah, so what you're going to find is that the acceleration in the x direction is 3.04 meters per second squared, because that's units of acceleration. And so this was one of the things they were looking for. They wanted us to find the acceleration while on the incline. So this is your acceleration while on the incline. So this is your answer to the first part, I guess. And what we want to do is now use it in order to find the velocity here. So notice they tell us in the problem that we're going to have to use it to, let me find it. Yeah, so it comes to some velocity v, and that's the velocity v we're going to solve for. Because if we want to be able to solve for the acceleration here, or sorry, the distance traveled here, we're going to need to know the velocity here. So hopefully that makes sense. You'll see why we need it in a bit, but let's go ahead and solve for it now. So now to solve for this v velocity, the way we're going to do it is by using kinematics. So kinematics in one direction, pretty simple. Hopefully you remember your kinematics, but the way I always like to do it is to write out my given, and I write down all the variables we know and what we're solving for. So we know delta x is a variable. We know v sub 0. We know v, we know a, and we know t. So these are our variables, and we're going to want to solve for the final velocity v. So at the end of our interval, which is at the end of the incline, that's what we're solving for. And so let's write in the variables we know. So as I said before, we just found the acceleration along this incline, 3.04 meters per second squared. We know the initial velocity. They tell us we're traveling at 5 meters per second. So cool. And then we need delta x. They tell us that too. They tell us how long the incline is. It's 110 meters. And then time we don't know, but we're not going to use it. So notice we have 3 kinematic variables and we have one we're solving for. So we do have enough variables to solve. The equation we're going to use is this one right here. So hopefully you remember your kinematic equations, but we're going to use v squared equals the initial velocity squared plus 2a times delta x. So we know if we square root both sides, that'll cancel this. So v is going to be equal to the square root of our initial velocity, which is 5 squared, plus 2 times a, which is 3.04, times delta x, which is 110. So all we got to do is just now plug this in. So second square root, 25 plus 2 times 3.04 times 110. Cool. So you're going to find that it is 26.34 meters per second. So we have the velocity here. And now what we're going to want to do is I'm going to show you why we needed it. So to find delta x, again, it's going to be another kinematic problem. So we're going to do that one up here. So if I write given, and then I write out my variables again, delta x, v sub 0, v, a, and t. So in order to solve for delta x, we're going to need 3 of the variables, right? Because delta x is basically this x here, or the change in our distance, how far we're going to travel. So delta x is our unknown, and we just found the initial velocity because we're doing it based on this interval, right? From the beginning of the x to the end. So we need to know the velocity here, which is what we just found, because this is the velocity at the end of this interval, or the beginning of the one we're doing right here. So this value is 26.34 meters per second. So v is going to be the final velocity, which we know if we're coming to a stop, because there's going to be a coefficient of friction, eventually we're going to stop and it's going to go to 0. So this right here is 0 meters per second. And then the acceleration, that's why they want us to find it, because we need the third variable, because we don't know time, in order to solve for this delta x. So that's why we're solving for these a's, in order to get another variable to actually be able to solve this kinematic problem right here. So now we're going to solve for this, and the way we're going to do that is by doing another free body diagram, but drawing it on here. So this is our guy now, and what are the forces acting on him at this point? So we know we're going to have the force due to gravity, mg. So luckily this one's not on an incline, so it's a bit easier. So mg, going straight down, are the force due to gravity. Obviously we have the normal force again, which points straight up. And then in the x direction, we have the force of friction, which just points straight this way, because we know we're traveling along this incline this way. So opposite of motion. So the force of friction is this way. So once again, we're going to sum the forces just like we did in the other one. So let me go ahead and do it right here. So summing the forces in the x direction is what we're going to start. And so we know the sum of the force in the x is going to be equal to ma of x. So when I'm talking about x, keep in mind I'm referring to just this way, and then the y is this way now. So just perpendicular to the direction we travel. So summing the forces in the x, ma of x equals, and so notice the only force in the x is the force of friction, and I'm going to consider left negative. Therefore, it just equals minus force of friction. Notice gravity and the normal force are both in the y, so there's no component from gravity like in this one in the x. So makes it a lot easier. So ma of x equals minus the force of friction, which we know is equal to mu sub k times F sub n. So how do we find the normal force again? Summing the forces in the y. So once again, forces in the y equals 0 because we don't accelerate or move in the y direction. So 0 equals, and then adding the forces. If it's up, I'm going to say it's positive. If it's down, it's negative. So F sub n minus mg. So F sub n is going to be equal to mg. So this tells us the normal force is just mass times gravity, which should be pretty obvious since it's the only force in the y. But yeah, so we know ma of x equals minus mu sub k times mg. Notice that the m's will cancel. So a sub x is just equal to minus mu sub k, which along this incline is 0.15. So different value because we're on a different part, times g, which is the gravitational constant, also known as 9.8. But yeah, so just plugging this in, minus 0.15 times 9.8 is a sub x equals minus 1.47, and then this is going to be meters per second squared. So this is your answer to another part. They're asking the acceleration along this incline. So minus 1.47 meters per second squared, which obviously indicates we're going to be slowing down. And yeah, so that's going to be the answer to, or the acceleration along the other incline. And now we've actually got it to solve for this distance. Because obviously this is the acceleration, as I explained before, for this part right here. And now we have three variables, so once again, just solving a kinematic equation. So the one that we're going to use is going to be the same one. V sub 0 squared, or v squared, the final velocity, equals the initial velocity squared plus 2a times delta x. So v is 0, so 0 squared is just 0, equals the initial velocity squared, so 26.34 squared, plus 2 times a, which we found was minus 1.47, times our delta x. So solving this, we would just minus this to the other side, and make sure it's squared, and then we would divide by this. So divided by 2 times minus 1.47 equals the delta x. So plugging this in, 26.34 squared divided by 2 times 1.47, you would get delta x, or your change in x, is 235.98, so about 236 meters would be the change in x. Yeah, so 236 meters is going to be the change in the x, which is basically right, how far we traveled this distance x. So this would be your answer for x. You could write delta x or just x, it doesn't really matter. It's basically just how far we travel along that flat incline, about 236 meters. But yeah, so this is your x, and then these are your accelerations along the incline. This was the flat incline, and then this right here was the incline with a slope. But yeah, so just a multi-step problem where we had to use kinematics and just summing the forces, but hopefully it made sense. And yeah, so these are going to be your answers, and hopefully you found this useful.